Okay, and we're back. Sorry for some technical difficulties there, but hopefully we can pick up where we left off the last time. So let f of x be a continuous function with values given in the table below. Determine the smallest interval in which the function must have a root. Alright, so taking a look at this, the key component, and then as you see it underlined right here, is that it's a continuous function. What does that allow us to do? We can use the intermediate value theorem. So while we might have this crazy looking graph, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. I'm not so concerned on these being labeled appropriately on this grid line, but notice -5 you have 1.25, so let's say it's somewhere here. -4 is 2.03, so something like that. -3 would be 3.05, and I'm not saying you actually had to graph this, I just want to try and illustrate some things. And then you have 3.01, and then you have something that gets really close here, and then 0 is back up to 7.99, so let's say it's way up here. 1 is 2.17, so maybe somewhere in there. And then 2, we went to -1.52, so we'll say somewhere there. -4.78 for 3, so we'll go maybe down here. -0.8, so right there. -10.7, so maybe way down here. -4.32, so something like this, and then -6.18, somewhere like that. Now, granted, we have a whole bunch of gaps here, and we have to draw lines that we can't pick up our pencil. So where are we guaranteed in terms of when we're going to cross? Now, I can go up way high, and then I can come back down. I can go way down low and get real close. I might even cross, but I'm not certain. That's the thing. And so all this, the graphs in between, is a question mark. But there's one spot in particular that we know we have to cross. We have a negative and we have a positive. Okay? So good. Glad to have you back, and hopefully math will be a little bit more fun this time around with a good old beverage in hand. So yeah, now taking a look at this, you have a positive and a negative, and what's going to happen is 0, we're looking when that y value equals 0, well, that's going to happen somewhere in this interval here. So determine the smallest interval in which the function must have a root. We can't go any smaller than it because we don't have enough information to say it's smaller, and it might very well happen in this interval, right? It might happen in this interval. Who knows? But the one we can guarantee is that interval 1, 2. And that's the only one we can guarantee by the intermediate value theorem. Okay. So hopefully that makes sense on that part. If not, let me know. And now we're moving on to epsilon and delta. What the heck is that junk, right? We see a lot of this stuff and what's going on. It really, it can be tricky at times. So let's say let's say this function here is f of x, right? So let's say we wanted to look at the limit as x approaches 5 of f of x. In terms of showing this, what happens, what we do is whenever x minus 5 we say is less than some delta, then we have this f of x minus whatever the limit might be. Oh, sorry for that. And what is that value going to be? Is it 5 as well? No, I didn't want to do 5, I'm sorry. Let's do 7. Limit as x approaches 7 instead of 5. Whenever x minus 7 is less than delta, f of x minus 5 was the y value, is less than epsilon. So we find. So you see all this junk and it's like, what the heck's going on? Well, here's the idea. you have around 5, you're going to have this band 5 plus epsilon and 5 minus epsilon. And what actually happens, oops, is when you look at the graph over here, don't let your eyes fool you. We're drawing straight lines right there. When you look at that graph, we're trying to see what values around 7 do we need in order to keep it within that epsilon. And so notice, if I were to draw this down, and we were to draw this one down, here's the trick. With the delta, we're looking on both sides here. Whoops. I don't know how I dragged that. I'll shoot. If we line that back up. Okay. So we have 2 parts, and then 7 is the dividing line. Which one is delta? And what we always want to choose of these 2 bands when we're kind of going, you want to choose delta to be the smaller one. And what we're kind of, when you think about this, oh, that was a little bit off. Let me see if I can adjust that. Sorry for the drawing being a bit off now. That was supposed to be centered around 5 when I drew it back up. Basically, I can fix it real quick. Well, hopefully you get the gist. What we're saying is there's going to be some error involved with these limits. And when we say this closeness property, so this would be the 5 minus epsilon, this would be the 5 plus epsilon right here. And so let's just say it crosses back there. And that one crosses right there. Okay, so you want delta to be the smaller of the idea because you want to keep it within that band. And all it's dependent upon is these epsilons. And so we're going to do this over and over again. And what we're trying to do is basically handle this error tolerance. This epsilon is basically some error off of 5, and then how close will we have to keep the x values in order to be within that error. That's all there is to it. So error being ER, so ERROR, not AIR. So that's essentially what this epsilon delta business is. Okay. So let's take a look at a problem as to what happens here. Let me change that to a blue. Okay, let's say we have the limit as f of x equals 1 minus x, and prove that the limit as x approaches -4 of f of x equals 5. Okay, so how do we actually go about the proof? Well, first we need to deal with delta and epsilon. So first off, we have this -4 sitting right here, and that's going to be our limit. And notice we have that this value right here is 5. Okay, so same song and dance. In terms of what we want our epsilon to be, I'll show you a general example. Now, linear equations are a little bit easier than others. So if we chose epsilon equal to 1, here's what that would look like. So we go down here, we reflect it on down, we go down here, and we reflect it on down. So notice in this case the distance is 1, and in this case the distance is 1. In fact, when you have linear equations, the distances will be the same on both sides. So there really isn't much thrill in these type of problems. And notice for the 5 minus epsilon, we still get delta in this case would equal 1. Let's go through another scenario. Say we did this now at the half mark. What's going to happen down below? Well, if we did 5 minus epsilon 1, where epsilon equals 0.5, this would be 5 plus epsilon 1, where epsilon 1 equals 0.5 as well. Notice our delta shrunk in half as well. And so what we want to do is people can pick whatever epsilon they want. They can pick 0.5, they can pick 1, they can pick 10, they can pick, usually they want small numbers though, like 0.01. We want to tackle all of those at once, no matter what error we're going off of the 5 on the y values. So keeping that in mind, here's how we actually work with it. So we want to start with f of x minus 5, and we want to assume that that's less than epsilon, and we want to try and find the delta. Then when we prove it, we actually go kind of backwards and just write it up. So f of x minus 5, that means that we have 1 minus x minus 5 is less than epsilon. So notice this becomes 5 minus x is less than epsilon. What we want an x minus 5 is less than delta, in terms of epsilon. So notice 5 minus x, the real trick here is multiply both sides by -1. That won't have any effect because the absolute value of -1 is +1. So notice that is the same as the absolute value of negative 5 minus x, and we're assuming that that's less than epsilon still. And so notice you get x minus 5 is less than epsilon. So that is going to be equal to our delta. And we'll do one that's going to be a little bit harder here next. So in terms of a proof, what actually happens? Well, so if you're to write up a proof of this thing, for any given epsilon, we can find the delta. In fact, they're equal in this case. So let epsilon be greater than 0. And assume delta equals epsilon. If the absolute value of x minus 5 is less than epsilon, then we need to work with the function f of x minus 5. So then absolute value of f of x minus 5 equals 1 minus x minus 5, which equals, how can we break that apart? Well, that equals the absolute value of 5 minus x, which is the same thing. And here's kind of the tricky part. Notice that's going to be the same thing as -1 times x minus 5. And since we're in an absolute value, we can pull out that -1. So this equals -1 absolute value times x minus 5 absolute value. And so in this case, the absolute value of -1 is 1, so this is equal to x minus 5, which is less than epsilon. Now, so notice we have f of x minus 5, a whole string of equalities, and then we finish with less than epsilon. And that's essentially all we did. We just basically worked backwards. That's how you write up the proof. I'm not going to be a stickler on writing up the proofs, but finding that kind of wiggle room with delta is going to be a tricky part that we need to kind of go through. And I'll go through the toughest scenario where most people struggled was what happens when we have a quadratic. So if you have this quadratic f of x, we want to find a delta such that f of x minus 9 is less than epsilon. Okay. Oh, yeah. So well, I'll come back to this in a second. So there's going to be a little caveat that we have to work with. If you noticed before in that first drawing, we had a little bit of gaps. The deltas were different, and that's because you had a quadratic, essentially. So in this case, oh, okay, so question before, why 5 minus x? Well, oh, did I write that wrong? Oh, I'm sorry, I don't know why I did 5 minus x. I was making all sorts of errors there. Sorry, that was a total error on my part. Got a little ahead of myself. So this is, let me mark this out. Yeah, it's not 5 minus x. I don't know why I did that. F of x minus 5. I wanted an x plus 4 less than delta. Sorry about that. And great catch. Shoot me another email. I'll give you extra credit for that as well. So when I'm looking at this, I don't know why I was doing x minus 5 for some reason. So this limits as x approaches -4, so that means x minus -4 is what we needed less than delta. So sorry about that. In this case, we want x plus 4 to be less than delta. So changing that up, when we did f of x minus 5, 1 minus x minus 5. Yeah, I was thinking ahead of another problem. Sorry about that. So 1 minus 5, notice that's going to be -4 minus x. So we can factor out, and that becomes, well, let me write this. -1 we can factor out, that's 4 plus x. And this would have been 4 plus x instead. Sorry about that. So let epsilon greater is still the same thing. At the end of the day, we have less than epsilon. So this is x plus 4 less than epsilon, which equals delta. Let epsilon be greater than delta and assume delta equals epsilon. So now, if x plus 4 is less than epsilon, then f of x minus 5 equals. So when we got to this point, that should have been, and that was my error totally, -4 minus x. And so this should have been -1 times x plus 4. And that's -1 times x plus 4. And this means x plus 4 is less than epsilon. And still we have the same thing at the end of the day. I just screwed up totally on the numbers. I was thinking back over here with the 5s for some reason. So get my mind back in the game here now. With this one, the x minus 4 and f of x minus 9, what happens? So we want to find what value does this. And thanks again for the, hopefully, does that make sense? I just made an error in terms of the 5 minus x. But yeah, shoot me an email. You get 2 bonus points tonight. In terms of what happens here, let's take a look. So we have f of x minus 9, that's x squared minus 7 minus 9 is less than epsilon. We want, so the limit as x approaches 4, that means we want x minus 4 is less than delta. So what happens here? Now in this one, you get x squared minus 16 is less than epsilon, and then we can break this up into an x minus 4, x plus 4 absolute value. Okay, so that thing's less than epsilon too. Now we have our factor of x plus 4 or x minus 4. We can rewrite this as absolute value x minus 4, and since we're taking an absolute value, we can take an absolute value h1. Now here's the difference. We want to kind of work with delta. Now if you notice back 2 times ago, what did we say? We want delta to be the smaller value, right? So since we're talking smaller values, what do we do here? Well, we can set a restriction on this absolute value of x minus 4. And what do I mean by that? Well, let's say x squared minus 7, just to give you an idea. We go here, and then we're shooting up, and we're shooting up like that. Okay, so we have this graph. What happens here? Well, you usually, if you're looking for to be close to 9, so let's say 9's up here, and we wanted to approach positive 4 in this case. So say this is what's happening. Usually we'll have people choose epsilons that are close to 9. So you want the 9 plus epsilon and the 9 minus epsilon going on here. And we can reflect that on down and so on and so forth. But once in a while you'll get the person that's being kind of a smart aleck, and they'll say, well, I'm going to choose epsilon to be 10 million, right? And notice what happens. In that case, epsilon goes way down there and it goes way up here, right? So we want to, and I'm glad to see your universe is intact again. That's good. What we want to do is we want to kind of avoid that case. Basically, when it extends beyond the graph, that's kind of silly. So what we'll do is we'll put a cap on our delta. And what do we mean by the cap? Well, we'll make an assumption here, and it doesn't have to be 1, but I'll actually toss it in as 1 just because the math is easier. It's pretty common. Assume that the absolute value of x minus 4 is less than 1. Then, what happens with this? Well, first off, what does that imply? That means negative 1 is less than x minus 4, which is less than 1, which means negative 1 plus 4, so that's going to be positive 3 is less than x, and that's less than 5. So in that case, if we have that restriction, so I'm going to star this as many times as possible. That's one thing that we're going to have to take note of. In this case, we want the absolute value of x minus 4. Well, what is x plus 4? Well, that's pretty simple. Just add 4 to every term, so you get 7 is less than x plus 4 is less than 9. So x minus 4, in the worst case scenario, the largest number it could be multiplied by is 9, right? So x minus absolute value of x minus 4 times 9 is less than epsilon. Okay, so now what happens? Well, you get x absolute value of x minus 4 is less than epsilon over 9. Okay, so now there's two things to consider. If epsilon is real small, say it's 0.001, notice you get 0.001 divided by 9. However, if someone chooses epsilon to be huge, say a billion, right? For those silly cases, notice we have that this is less than 1. So at the end of the day, what happens is let delta equal, remember we always wanted the smaller, so the way we write that is the minimum of 1 and epsilon over 9. And so if we don't have to consider the funny business, right, of say someone choosing something very large, we don't even have to write the minimum. We can just focus on epsilon over 9 if people are choosing that small margin of error involved with epsilon. So that's the whole idea of epsilon delta. Sorry for the little hiccup there on the previous one. I don't know what I was writing for x minus 5. It was always x plus 4. And the way you can always determine where you're going, whatever the limit is, so this number here, let's say in general, if you have limit as x approaches c of f of x, you want factor of x absolute value of x minus c from, and let's say this equals L, from the absolute value of f of x minus L. Okay? So you got the epsilon delta stuff out of the way now, and let's get on to where the big chunk of change of this course is derivatives. And so I want you to be aware as to what we'll be doing when it comes to derivatives. And so we'll take a good look at this stuff. So is it possible to find the slope of the tangent line of a smooth continuous curve f of x at the point A? So here's what happens. You have this point A sitting right here. And what we can do, rather than draw the tangent line and try and make a guesstimate, we can use this notion of limits. And so what we'll do is we'll first say, hey, we'll take some other point, and let's call this x. And so we'll have, if this is x, the coordinates here are x, f of x, and the coordinates of this are a and f of a. And if we were to find the slope of this, let's say, secant line, how do we do that? Well, you go f of x minus f of a all over x minus capital A. But what we want to do, we don't want secant lines, we want tangent lines. So what do we want to have happen? Well, we want this x to get closer and closer to that a, technically from both sides. So what we'll do is we'll take a limit as x approaches a. And this should be the slope of our tangent line. And this is actually given a special notation. It's f prime of this capital A. Okay, this stands for what we call the derivative of f at the point A. In a similar manner, now the more familiar one for a lot of people, so you have this point A comma f of A, f of A, and what we want to do, we want to slide it over just slightly and draw that secant line and get closer and closer to a tangent line. And we're going to do it so slightly, we'll put a plus h. And so that means that this coordinate here is a plus h, comma, f of a plus h. So just another notation, that's all. And so in this case, if we find the slope of the secant line here, it's f of a plus h minus f of a so I see no problem, but the homework asks for a numeric value. Can you explain how we get to that with the quadratics? I'm assuming are you talking derivatives in that case? If so, I'm about to touch on a problem with derivatives and quadratics. If you're talking back about the epsilon delta, let me know and I can go back there. So in this case, for the derivative, I have a plus h minus that a. And what happens? Well, this simplifies to just f of a plus h minus f of a all over h. Now what we want, though, is we want to take a limit. We want h to get closer and closer to that a, and the way you do that is you take a limit as h approaches 0. And so this whole thing, take the limit as h approaches 0, and this is the more common derivative, and that's what we call f prime of a. So yeah, just let me know if you're referring to the epsilon deltas on the quadratics or if it's the derivatives with the quadratics, because I can go back and I can also touch on the derivatives as well. So in terms of the derivative, though, this is your formula. You can use either one when it's derivative at a point. In general, though, we're going to try and find a derivative of a function. That's what I'm going to try and lead to here tonight. Alright. Find the slope of the tangent line at x equals 3 for the function f of x equals x squared minus 2x minus 8. So it's nice to have things along the lines of how you're actually going to approach this thing. So I'm going to show you both methods. So first case, we're looking for as it approaches 3. So limit as x approaches 3, we can do f of x minus f of 3 all over x minus 3. The other case is the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. And I'll kind of show you how both work. First things first, either case we're going to need f of 3. Okay, so f of 3, notice we get 3 squared minus 2 times 3 minus 8. And so that'll be 9 minus 6. So that's going to be 3 minus 8, so that should be negative 5. Okay, so I'll finish this question real quick, then I'll go back to the epsilon delta in terms of homework asks for a numeric value in terms of what's going on. And so I'll kind of show you how that works as well. So yeah, moving forward with this, and then I'll go back to the epsilon delta real quick. In terms of what we have, f of x, what is f of x? Well, f of x is equal to this junk right here. So you have, this is x squared, oh, I needed the limit as x approaches 3. Of x squared minus 2x minus 8, then minus a negative 5 all over x minus 3. And so notice we get what? So that becomes x squared minus 2x, and then when you have a plus 5, so that would be minus 3 all over x minus 3, and we want the limit as x approaches 3. Okay, so hopefully if we've done things right, the 3 should, there's a, the 3 should cancel out. Yeah, so there's a delay on the chat, no problem. Sorry, I'll just kind of wait and kind of keep an eye on it as it's coming in. So as we're moving forward with this, limit as x approaches 3, we can factor out the top. Goes x plus 1, x minus 3, and then x minus 3. X minus 3's cancel. You're left with the limit as x approaches 3 of just x plus 1, and so that equals 4. Okay. Now let's try the other one. So you have f of 3. I'm going to actually calculate f of 3 plus h right down here. And notice that is 3 plus h, the quantity squared, minus 2 times 3, minus 8. Oh, 2 times, sorry, 3 plus h, minus 8. Okay, so where do we go from here? This is 9 plus 6h plus h squared minus, this is where most people trip up. They'll write this as minus 6, but they'll most likely write plus 2h, but it's actually minus 2h because you got to distribute that minus 2, then minus 8. So then what happens is we already have f of 3 up top. Notice that equals negative 5. I'm actually going to write this as f of 3 plus h minus f of 3 down here. So we can do this all kind of on one line. Notice that's 9 plus 6h plus h squared minus 6 minus 2h minus 8. And then all of that, we go minus negative 5. Okay, so taking a look at this, what happens? Well, notice 9 minus 6 is negative, or positive 3, then minus 8 is negative 5. So if you take all those numbers, it crosses off with this. And actually, if you have polynomials, just a kind of quick lesson for you, the constant terms should cancel out, to be honest with you. So if you can tell if you're making a mistake on the process. So as long as you're dealing with polynomials. So this whole thing equals 6h plus h squared minus 2h. So our limit as h approaches 0 is of 6h plus h squared minus 2h all over h. Notice in the numerator you can factor out an h on each term. So you have h times the quantity 6 plus h minus 2 all over h. Your h's now cancel. And then we can just plug in h going to 0, so you get 6 plus 0 minus 2, which equals 4, and that matches our other answer, right? So two different ways to kind of get at the same answer. Personally, my preference is the second one just because it coincides, but it doesn't mean I haven't used the first one from time to time. So hopefully that makes sense on that. If not, let me know. I will go back though to the part on the epsilon delta. Okay, so taking a look at this, the question was, the homework asked for a numeric value. Can you explain how we get to that with the quadratic? So you want a numeric value. So there's two different ways you can do this. So I think if you're referring to like a problem 5, I believe, in the homework, 1/9 epsilon would be the other way you could write that. So 1/9 would be your constant. So I'll give you all sorts of examples if you like. Assume, let's go, instead of here, we'll go absolute value of f of x minus 9 is less than, say, 1/7. Right? Well, I know immediately that delta equals the min of these two. So in terms of our delta corresponding to that, epsilon equals 1/7. Well, delta equals the minimum of 1 and 1/7 over 9. Well, that's just 1 over 63. So delta has to equal 1 over 63, and that'll do the trick. Okay. If I change delta to, well, let's see what happens here. We'll do 1 over 11. Well, the only thing that changes in our delta equation is we get 1 over 11 over 9, and so that's 1 over 99. Okay. And if you had some goofball do something like, oh, I want this to be less than, say, 7,000, and you won't see that though. The homework doesn't ask it like this case. So what would happen is the minimum of 7,000 over 9, but remember we set 1 as that restriction, so it's just going to be the min, it's going to be 1. Okay. Please let me know if there's a question on that part. Hopefully that makes sense. But yeah, for the most part, you're having these f of x minus 9 would be less than, say, for example, 1. And then you get 1/9, and then so this is 1/9, things of that nature. That's the more common sort of trait. But notice we have answers for every single scenario, regardless of what epsilon is chosen to be. So that's why we try and solve it in general, no matter what that margin of error is that you're looking off of the y value. That's what we're going there. Okay. So yeah, if you're doing okay with derivatives, that's awesome. I was going to try and get to the graphs, and you can check out. I'll still do the rest though for the rest of the class and whatnot. So the next part that we're looking at, find the derivative function. And how do we do that? Well, we just change, instead of having a number in where we had that a plus h or whatnot, we're going to change that to an x. So in terms of what's going on there, what we end up getting would be something like this. Limit as h approaches 0. Well, we need to find f of x plus h and f of x. So f of x we already have. Oops. So we need f of x plus h. And so that would be x plus h, the quantity squared, minus 2 times the quantity x plus h, minus 8. Okay. So with that in mind, we can simplify that a little bit. So we get x squared plus 2xh plus h squared minus 2x minus 2h minus 8. So now if you take f of x plus h minus f of x, get ready for our fire sale here. So you get x squared plus 2xh plus h squared minus 2x minus 2h minus 8 minus x squared minus 2x minus 8. So what happens? Well, your x squareds, they're gone. Your 2x's, notice you have a negative 2x and another negative 2x that we're subtracting, that's gone. And then you have an 8, and that's gone. And that's what should happen anytime you have a polynomial, right? So you have, every time there's a polynomial, all those things should just cancel, and we're in good shape. So this should be the limit as h approaches 0 of f of x plus h minus f of x all over h. And so that equals, well, we simplified that to 2xh plus h squared minus 2h all over h. And we need a limit as h approaches 0 of that thing. So this equals, the limit as h approaches 0 of, we can factor out an h from the numerator, so you get 2x plus h minus 2 all over h. And so notice we get, in this case, the derivative, which we shall denote by f prime of x, equals, well, plug in h equals 0, so that thing goes to 0. So we're left with just 2x minus 2. So what's the big deal, right? If you look at the previous one, notice we were looking for the tangent line at x equals 3, right? And we found our answer was 4. Let's check this out real quick. So if we go f prime of 3, notice we plug that in for the x in our derivative equation. That's 2 times 3 minus 2. Notice it equals 4. Now I could also, rather than making us go through a whole nother calculation, I can ask you tangent line, slope of the tangent line at x equals 7. I could just plug in 7 into that derivative equation and I have the slope of that tangent line. So that's the beauty of this stuff, is you can go through that. Now on top of that though, we have that function. I'm going to erase this part right here just so I can draw a graph. Let me illustrate what's happening graphically. Okay, so x squared minus 2x minus 8. What is that factor? So that's x plus, or x plus 2 and x minus 4. So we'll go 1, 2, 3, and 4, and then we'll go 1 and 2. Those are our zeros. So that means the midpoint, which should be 1, when we plug that in, that should be our vertex. So you go 1 squared minus 2. So 1 minus, well, essentially 10, so that's negative 9. 1, well, here, let's do this. 1, 2, 3, 4, 5, 6, 7. Let's do 8, and let's do 9. Right there. So I know I shortchanged in terms of each y value is going to be only 1 unit, whereas the x values are going to be 2 units at a time. So it'll have a strange shape, but hopefully get the gist. So when you get this, and we plug in, we get negative 8. So that goes right there, and then keeps on going up. I want to emphasize a couple things. So there's the graph of the function f of x. Notice that f prime of x equals 0 when essentially 2x minus 2 equals 0, so x equals 1. Okay? So at x equals 1, you get this graph. Now, 2x minus 2, if I have that being, so if I had y equals 2x minus 2, what happens? Well, at 0, you'd have this, and then we're kind of increasing. And we're increasing faster and faster. So we're going to draw a graph. It has to be a straight line. It looks something like that. So, and I can continue this on down and continue it on up. But look what's happening. Here's your relationship that we're going to get into. The graph of the function is falling all the way until it hits this point. And what happens at this point is you have, let me use a different color. So you have a horizontal tangent line right at that point. Meaning the slope of that tangent line has to be 0. And then it starts to increase. Well, as it's increasing, if I draw any tangent line here, touches it just at that one point. Notice the slope is positive, and so the graph of the derivative has to be increasing. That's the relationship that you're going to be seeing between derivatives and the original functions. If the graph of the original function is increasing, your derivative will be positive. If the graph of the original function is decreasing, your graph will be of the derivative will be negative. in terms of the y value. And if it's a what we call local max or a local min, that's when your derivative will actually equal 0. Okay, so we can actually start talking about maximizing and minimizing things. Very useful for econ majors, right? Trying to maximize profit, minimize costs, things of that nature. So hopefully that makes sense on that one. Now let's get to a harder one in terms of calculating the derivative. So find the derivative of the following function and use it to find the equation of the tangent line at x equals 3. So remember that this limit as h approaches 0 of f of x plus h minus f of x all over h. We got to figure that out. So first off, on this thing, f of x plus h equals the square root of 4 times x plus h minus 3. We might even want to expand it here, so you get 4x plus 4h minus 3. Oops, plus 4h, sorry. Okay, and then f of x we already have, but let's do this. So f of x plus h minus f of x has to equal square root of 4x plus 4h minus 3 minus the square root of 4x minus 3. What does this thing look like then? Well, this is the limit as h approaches 0 of square root of 4x plus 4h minus 3 minus the square root of 4x minus 3 all over h. Where the heck do we go from here? Well, this goes back to your limits. How good are you with limits? Well, and by the way, all of this equals f prime of x. So the limits, what we need to do in order to do this one is conjugate, because we have those two roots in there. So 4x plus 4h minus 3 plus the square root of 4x minus 3, all divided by square root of 4x plus 4h minus 3 plus the square root of 4x minus 3. So what happens up top? So this goes limit as h approaches 0 of, well, notice we'll square the first term, so you're left with 4x plus 4h minus 3 minus 4x minus 3, just by that property of conjugation. And then we have down below an h times the quantity, we have a square root of 4x plus 4h minus 3 plus the square root of 4x minus 3. And that might seem a lot nastier, but if you notice in the numerator now we're canceling off the second bits of terms, right? That's important. So we're left with the limit as h approaches 0 of 4h all over h times the square root of 4x plus 4h minus 3, and then plus the square root of 4x minus 3. And now we're ready to do some work. So we can cross off the h's, and then we can plug in h equals 0. So we're left with 4 over the square root of, notice this for h will go to 0. So you get 4x minus 3 plus the square root of 4x minus 3. So how many 4x minus 3's do we have? Well, so we get the derivative equals 4 over 2 times the square root of 4x minus 3, which happens to be the same thing as 2 over the square root of 4x minus 3. Wowzers. So now, taking a look at this, where the heck do we go? Well, it says that's the derivative, so that's one part, right? We want to find the equation of the tangent line at x equals 3. So slope of the tangent line equals, so we can find that by plugging in f prime of 3. So plug in 3 into our derivative. So we get 2 times the square root of 4 times 3 minus 3. So that's 2 times the square root of 9, or 2 times, I'm sorry, 2 divided by the square root of 9, which is equal to 3. So our slope of our tangent line is 2/3. Now, you need a point on the tangent line. And that's where we already have 3 as the x value. We just need the y value. So we go 3, and then we need to plug that into the original function. So that should be square root of 4 times 3 minus 3. And so that equals square root of 9, as we just mentioned, which equals 3. So you have this point 3 comma 3. So the tangent line can be found just using the good old point slope formula. So our tangent line is given by y minus our y1 is 3, which that comes from our point there, equals m, which is the slope of our tangent line, 2/3, and then it goes x minus the x value of our point, which is 3 as well. And you're done. So hopefully that made sense in terms of the derivatives, tangent lines, and all that jazz. If you have any other questions, please post them in the class discussions or send me an email, or we'll do another YouTube live session, and hopefully with a lot less hiccups and whatnot in terms of the technology. So sorry for what happened tonight. But yeah, if you have any other questions, just let me know. You can also stop by office hours as well. So starting Friday, I'll have some too. Okay, hope you have a good night, folks.